Welcome back. We're going to talk some more about complex matrices, Hermitian and now unitary matrices. I think it's quite helpful to go back to Rn and refresh our memory about symmetric and orthogonal matrices. This will be a little bit repetitive, but I think it's a good idea to get it all down in one place, and there are a couple of new ideas here. So remember, we've talked a lot about the inner product. VW is V dot W, or V transpose times W. This inner product is symmetric. It satisfies VW is equal to WV. If you switch the order, it doesn't change. And of course, this is an extremely useful operation. We talk about orthogonal vectors and so on. We use this quite a bit. Now, there are other inner products which satisfy similar properties. You don't just have to use the dot product. Consider the following. Suppose I defined VW to be V transpose X times W. So it's just like the usual inner product, except I've stuck this X in the middle. Well, if you take X to be symmetric, then WV is W transpose XV, and this is a number. And remember, every number is its own transpose. So I can take the transpose of this, and I get V transpose X W transpose transpose, which is W. And so you see that WV is equal to VW. So that's the whole point, well, the main point about symmetric matrices. Symmetric matrices give you different kinds of inner products. Symmetric inner products. Okay, that brings symmetric matrices into the picture. Now let's talk about orthogonal matrices. What's an orthogonal matrix? Well, the main thing about an orthogonal matrix is that it preserves the usual inner product. That is to say, if you have two vectors v and w, and you take their usual inner product, if it doesn't change when you use instead qv and qw, if these two numbers are the same, then you say the matrix is orthogonal. And I'm writing out the condition here. QV transpose QW is equal to V transpose QW. And I'm asking that that be equal to V transpose W. Well, the only way that can be true for all V and W is if Q transpose Q is equal to I. So that is the definition of an orthogonal matrix. And it shows you that the main point about orthogonal matrices is that they preserve the inner product. And equivalently, they preserve length, because the length of a vector is just expressed in terms of the inner product. So again, symmetric matrices define alternative inner products. Orthogonal matrices preserve an inner product. Okay, so let's look at some properties of symmetric and orthogonal matrices. Most of these we've seen before, but there are actually a few new ones. So let's start with symmetric. If you have a symmetric matrix, its eigenvalues are real. It's a basic property of symmetric matrices. And its eigenvectors are orthogonal. And of course, I mean eigenvectors with different eigenvalues are orthogonal. And a third property is that you can write any symmetric matrix in this form, Q, D, Q transpose, where Q is orthogonal. This is a new fact. We haven't seen this before. I'll come back and talk about it a little later. What about orthogonal matrices? Okay, the eigenvalues of an orthogonal matrix are plus or minus 1. I don't think we've seen this before. We'll come back and talk about that. And plus or minus 1, I'm going to write as the absolute value is 1. They're real, and the absolute value is 1. Again, eigenvectors with different eigenvalue are orthogonal. We haven't seen that before. It's a similar property to symmetric matrices. And the rows and columns of an orthogonal matrix are orthonormal. Finally, please ignore this determinant of U thing. This is a misprint. The fact is that the determinant of an orthogonal matrix is plus or minus 1. This absolute value of determinant is going to come in later when we talk about unitary matrices. Okay, so that was all a review of the real theory with a couple new facts, and now we're going to march through the corresponding things for complex matrices. So we talked about an inner product on a complex vector space. You put a bar on the V. And what symmetry does this thing have? If you switch the order, it's the same, except that it changes by the complex conjugate. You get this bar. This is called a Hermitian inner product. And remember, we defined the length of a vector to be the square root of VV. And this is a non-negative real number. And just like in the real case, there are other inner products which satisfy these properties. And you define them in a similar way. How do you define an inner product satisfying this thing? Well, you define VW to be V transpose bar times XW, where you put this X now in between the V and the W. And the condition that WV is equal to VW bar is exactly that X transpose bar is equal to X. That is to say, that's the Hermitian condition. So that explains why this is a natural kind of matrix. It defines an alternative inner product on a complex vector space. Okay, and going on now, what about matrices which preserve an inner product, the basic inner product V transpose bar W? Well, we write UV UW. If that's equal to VW, what does that mean? What kind of condition on U does that impose? So U is an n by n complex matrix. Well, let's write down the UVUW is given by this, and that's V bar transpose U bar transpose U times W. And I'm asking whether that's equal to V transpose bar W for all vectors. And just like in the real case, you conclude that this fellow here had better be equal to I. And so that defines a new kind of matrix. This is a unitary matrix. We say U is unitary if U bar transpose U is equal to I. So symmetric becomes Hermitian and orthogonal becomes unitary. So unitary condition is that it preserves the inner product, just like orthogonal in the real case. And of course, it also preserves lengths. So unitary matrices are kind of like rotations in a complex vector space. Okay, let's keep going, following our analogy with the real case. Let's look at the properties of these two kinds of matrices. Let's look at Hermitian matrices first. Well, we saw that they have real eigenvalues. That's a very important property. And that eigenvectors with distinct eigenvalues are orthogonal. That's also just like in the real case. And you can write X as UD transpose U bar, where U is unitary and D is diagonal. And again, this is a new property that we haven't talked about before. I'll come back to it. And the properties of unitary matrices, well, their eigenvalues have absolute value 1. So in the real case, this was plus or minus 1, and now it's a complex number of absolute value 1. The rows and columns are orthonormal. And again, the eigenvectors with different eigenvalues are orthogonal. So all four of the kinds of matrices we're talking about have this eigenvector property. Okay, so that's a summary of the properties and the analogy with the real matrices. So let's now talk a little bit more about unitary matrices. So a unitary matrix by definition is one that satisfies U bar transpose U is equal to the identity. So what's a 1 by 1 unitary matrix? Well, that's a number z, such that z bar z is equal to 1. The absolute value of z is equal to 1. And what about a 2 by 2 Hermitian matrix? Well, here's the condition. And if we write that out, we see a bar a plus c bar c is equal to 1. That says absolute value of a squared plus absolute value of c squared is equal to 1. That says that this vector has length 1. And the next condition you see is that AC BD is equal to 0, which says that the columns are orthogonal, and the result is that the rows and columns have to be orthonormal. So for example, if you have a diagonal matrix, it's orthogonal if and only if z and w have absolute value 1, which is to say they're of the form e to the I theta, e to the I phi. All right, now let's suppose you have a unitary matrix, U. The first property I've claimed is that the absolute value of the eigenvalues are 1. So why is that? Well, suppose uv is equal to lambda v. Simply take the length of both sides. The length of uv is the length of lambda v, and the length of lambda v is the absolute value of lambda times the length of v. And by definition of unitary, the length of uv is equal to length of v. So we conclude that the length of v is equal to the absolute value of lambda times the length of v. So that says that absolute value of lambda must be 1. This is supposed to be true for all vectors, and the only way that could be is if absolute lambda is equal to 1. Let's look at this orthogonal eigenvector property. Why is it that a unitary matrix satisfies this? Well, suppose you have two eigenvectors with eigenvalues lambda and gamma. And from the previous part, we know that they both have absolute value 1. Well, let's write down the unitary condition that says that VW is equal to UV UW. And let's see what this tells us. Well, that says that V bar transpose W is UV bar transpose UW. And now UV is lambda V, so I'll plug that in here. Lambda V bar transpose. And similarly, UW is gamma W, so I get gamma W. And this is V bar transpose lambda bar gamma W. I can pull the scalar lambda bar gamma out front. And these two things I'm saying are equal. Well, if V and W are not orthogonal, which is to say their inner product is not 0, that forces lambda bar gamma to be 1 for these two things to be equal. Well, we're supposed to get a contradiction. What's wrong with that? Well, look up here. The absolute value of lambda is equal to 1. Well, the absolute value of lambda being equal to 1 says lambda bar lambda is equal to 1. And you see the contradiction? Here I have lambda bar gamma is equal to 1. Here I have lambda bar lambda is equal to 1. Well, if you look at these, it obviously says that lambda has to equal gamma. But that's a contradiction. I was assuming that the eigenvalues were different. So if the eigenvalues are different, then it forces them to be orthogonal. All right, finally, let's look at the last property. I'm claiming if you have a Hermitian matrix, then you can write UX U bar transpose is D for some unitary matrix U. Or equivalently, I can write X as UD U bar transpose. Why is that? This looks familiar, this kind of thing. And this is actually quite easy. So let's suppose X has eigenvectors V1 through Vn, and with corresponding eigenvalues. And we know that these eigenvectors are orthogonal, and so we might as well scale them to be orthonormal. And then if we let this change of basis matrix S, with the V's being the columns, with that being S, we have Sx S inverse is equal to D. This is the standard way to diagonalize a matrix. S achieves this change of basis. But the whole point is that the columns of S are orthogonal. So S is unitary. What does unitary mean? S unitary means S bar transpose is the identity, or S bar transpose is equal to S inverse. So I can replace the S inverse here with S bar transpose, and I conclude SX S bar transpose is equal to D, and that's what I was trying to show, where here S is a unitary matrix. All right, I think that's an excellent place to stop. I will see you in class.